Hello, everybody, and welcome to Splunk B-Sides. I'm Michael Simko here with Ann-Drea Small, and we are going to be talking about using natural language processing to identify which of your searches are doing whatever you define as well. So we're looking for good practicing in our searching using NLP. Well, about us, I'm Michael Simko. I'm a longtime principal architect at Kinney Group, longtime Splunk instructor, professional services consultant, member of the Splunk Trust, one of the guys with the Phases running around if you run into us at events. And joining me today is Ann-Drea Small, who is the principal engineer and team lead of IT Operation Analytics at Kinney Group. Ann-Drea, you want to say hello?
Hi, everybody.
And you can see she's got a great listing master's degree in this field. So as somebody who teaches data science, I'm super happy to have somebody who is a actual practitioner of data science joining together. So I think together we're going to be the super team. As she laughs about that one, she's like, yeah, right. All right, we got 6 elements. There is a lot going on our slides. We are not going to talk through every slide in exhausting detail. Think of a lot of the slides as a jump for you to go off and look to go, oh, okay, I want to know more about that particular element. So then you're going to go off, dive a little bit deeper. We've got 6 big sections. We're going to start with just what is natural language processing. There's probably a few different ways you could discuss or define it if you were trying to make it up off the words. So we'll go through what we mean by it. We'll talk about the different algorithms that are popular with NLP. Then we're going to switch over to what we're actually going to do with it. So what's our objective? Next up, how to use it in the Splunk machine learning toolkit. We're making the assumption that most of us here are MLTK people or are Splunkers, and our normal way to access this would be MLTK. But I think what Ann-Drea's got showing us here is going to work in a lot of different fields. It's the logic concept and the decision making and what she's doing is going to be really what's going to be the more interesting piece, or at least the applicable to whatever you do in the future. Figure out where we get data. Okay, and just a little bit of sampling to show us how we get playing with it. All right, so Ann-Drea, what is NLP then?
So natural language processing is the ability of a computer program to understand the human language. Now, human language is done in many forms. For most interpretive purposes, we're going to look at the way that it's written. Most things about ML, the reason why natural language processing is so powerful is for a number of reasons. As society has become engrossed in social media, recommendation engines, different aspects of trying to figure out which text is more important in articles and headlines, and make suggestions on what you should read, watch, think, buy. Natural language processing is a part of our everyday life now. And so what makes it so powerful is the artificial intelligence behind it that processes it, converts it to code, makes the computer able to understand it, and then turns out output, recommendations or understanding of what is being written and said.
So this sounds, 1, super powerful, 2, super relevant to a lot more than just Splunk.
Yes. One of the things that makes it so powerful to Splunk is not only the way that we search, which is what we're talking about today, but also how Splunk can look at social media feeds and find out different things. One of the most powerful things is called sentiment analysis. That's what people usually associate with natural language processing, basically attributing sentiment or feelings or emotions or honestly happy and sad to what people are saying.
Okay, yeah, I've seen that with like tweets. Is this a happy tweet about the company or a negative tweet about the company?
Yeah, that's major. It's a new way of people reviewing. And so it's like, instead of saying, hey, I give you 5 stars, it means somebody has said something positive about you. And so not only happy and sad, but positive and negative. So a positive tweet is something that gives people honestly, they attribute it to how much you like their company and how much you respect their brand.
Very cool. All right. So we got what, 3 phases or 2 phases of natural language processing?
There's 2 phases. It's the data pre-processing, and then it's the algorithm development. That data pre-processing is the most important part. People think it's the algorithm because it's all the cool math with all the cool Greek symbols, but that data pre-processing, where you're cleaning the text, where you're making it easier for the computer to understand it, is it's the largest part. I mean, of any data science, it's the largest part. When you're taking data into Splunk and you're onboarding it, if you can't recognize the JSON and XML from your text, it'll be a lot of hurt trying to get through. That's why we spend so much time parsing that data before we get it into Splunk to begin with. That's that 80%. And so your data pre-processing is basically, the cleaning before you parse.
I've always heard in machine learning, it's about 80% of the data scientist's time is spent munging the data.
It is.
Which is preparing, cleaning, perhaps limiting fields, all that goodness.
It is. A lot of it is actually filling in data that doesn't exist. It's very hard to do it with like an empty data set, but a lot of times we'll fill in null values just so that we can get the data to go through.
Very cool. Speaking of that, you've got 6 types of data pre-processing up here. That was really interesting. I mean, you got a couple of these that are very common. Segmentation, right? Where you take large strings, break them apart. Would that also be where, well, we're doing natural language. If we were doing non-natural language, we'd probably get rid of all the crazy symbols and hyphens and underscores and things. But for natural language, man, we might want to keep some of those.
Spaces are big, hyphens are big. A lot of times we have compound words in English language, and so we keep some of those hyphens and colons in our text. It just depends. A lot of that makes sense is like, what period of time is this text from? If you're listening, if you're going to go through and parse through Charles Dickens' A Tale of Two Cities, you're going to find a lot of punctuation that you're going to want to keep.
Well, it was the best of times and the worst of times.
It was.
By the way, that was off the cuff for anyone listening. So, haha. I really hope it's from the right work.
It is.
See. Well, you got tokenization. All right, breaking down into smaller units, such as words. So if you had paragraphs or strings of sentences being written down. Stop words. I always find that one really interesting because there are so many meaningless words in the English language.
We have a lot of filler.
Yeah. And that could even be, well, I wonder, how often did they go after the other things such as and the things that people use almost as commas?
I like those words, like the ahas and the uhs and those things that we put in just so that we can pause and think about something else. Again, like your pre-processing is only as good as the person doing it. So if they're not aware that it's there, or if they are unfamiliar with it because it's not their primary language, then they're not going to get as much as somebody else.
Right. Yeah. And that's actually a really interesting one you just popped up there on the primary language, because as someone who teaches people around the world, I noticed there are different stop words from people coming from different language backgrounds. So somebody who grew up speaking Arabic has different stop words than somebody who grew up speaking British English. Let's have fun. All right. Other ones in here, we'll get diving into more things. Andrea, tell me about that middle one, lemmatization, because you had to tell me about this one.
Yes. So lemmatization, which is from the root word lemma, it's caused from, basically it's like different tenses and different versions of a word. So like for instance, the verb to be, you're going to have your were, was, is, are, am, has been, will be. And so all of these versions of the word be is kind of smashed down into one variation so that you're able to process it as one unit. So basically it recognizes the similarity or the meaning behind the word. And again, this is also based on whoever is creating this ability to lematize, because if they're not able to think of all of these variations, it's only going to be as great as they program their algorithms, their pre-processing rules to be.
All right. Mind if I keep chasing on this one? Folks, the reason why I chase on this is all the rest of these, absolutely I was ready for. And then I saw this one in the middle and it started diving into it once Andrea told me about it. And I was like, wow, it makes so much sense. Would this also then handle, say, nicknames? So what if somebody was discussing, there was a football game the other day and it was Bama, but then the other person describes him as Alabama. Do we do this for that too?
Yes. Not only do we do it for nicknames, but we also do it for acronyms. Like, for instance, we started calling natural language processing NLP. And so in order to make sure that, going forward, you're able to say, okay, this association is to this word, you have to be able to recognize that it's the same thing, because there's other NLPs out there. So you have to make sure you define it correctly.
Well, every acronym, yes. How many of us have ever gotten in trouble Googling the wrong acronym meaning? Yeah. All right, very cool. As I said, we're not going to dive through each one of these, but so, all right. What are you talking about here on algorithm development?
So algorithm development, you have your two main types, your unsupervised and your supervised learning. For natural language processing, which is your classic classification system, supervised learning is going to be where the majority of your algorithms are going to come from. Now that uses sorted data. So you already have a set of training data. And in that set of training data, you have categories that you've set up. For instance, cat, dog, and mouse. Let's go with those three. And you have new data that's coming in, and you decide whether or not a Doberman is a cat, dog, or mouse, or Shiba Inu, or lion, or a tiger. And you just go through and say, okay, all of these different things, which category is it closest to? And you're going to use your supervised learning algorithms to do that, because you already know these are the things that you want to fit it into. Now, the unfortunate side of that is, let's say you have something like a horse. Well, your three categories are only cat, dog, and mouse. So unless
we're in a little trouble, yeah.
So unless you want to take that horse and call it a cat or a dog, you're going to be, kind of have to go back and redefine your categories.
So it would either pre-process out the horse or up the category choices? Exactly.
And so that basically what probably would wind up happening is that it would wind up processing out because it's not close to anything else.
All right. Super interesting take on this. So also then on unsupervised. So unsupervised is we didn't prepare. Data just shows up and we're going to do something with it live, essentially, right?
Pretty much. It's like saying, hey, we have a ton of people who went to this event and we want to figure out if these people are going to go to which stall. And then those people go and they literally cluster around those stalls. This past weekend, I just went to the state fair here in North Carolina. And so, normally you're going to have people that go towards rides, people that go towards games, and you're going to have people that go towards food. Which people do you think are going to go to games, rides, and food?
Right. When you said stall, I was picturing which part of the restroom. I'm like, wow, this is interesting data.
That's funny.
All right. So top algorithms on NLP. So natural language processing. My first thought, anytime I hear language processing of any sort, I immediately turn to TF-IDF. Namely, because I think that's the approachable one that we tend to see as a layperson around data science. Is that where you head first, or is there the consultant answer of it depends going to be spoken often?
So So most people, and this is what I find, is that most people tend to use anytime they say, all right, I'm gonna do this aspect of machine learning, they normally just throw everything at the data and see what sticks, which I love because, you know,
You have figured out my pattern on data science. Or throw 13 different algorithms at it and see which one looked like it worked best.
the thing about CFID, IDF is that you basically are looking for how many times that word appears across, all your data sets, which is very powerful when you're using a tool like Splunk, because the truth of the matter is you're trying to find, like, let's say you have security data, and let's say you're looking for a specific server, and let's say you're looking for all the data that's going through all the servers. You're looking for that key term across all your data because you're trying to correlate a group of events that happen simultaneously. The same thing with NLP, like you're taking a word and you're trying to see how often that word has been mentioned to see how important that word is to a group of people. So let's say you see health documents, and COVID-19 is a word that you see very often, and you see it often in these health documents, and you see it often in the news, and you see it often at all the stores. It's pretty important if you see this word everywhere. Even before the pandemic closed down, we started seeing the word more often, and we became very aware that the word was that COVID-19 was becoming an important topic. And so even before we shut down, we knew it was getting worse and worse. And so what people have started to realize is that you might not have realized it, but a pattern was forming around you. And that's the same way how words are in documents. If the topic keeps getting talked about more and more often, whether it's in the news or around you or whatever, it's more and more important.
Oh, that's really cool. And yeah, it's neat to see those changes in retrospect. You can spot it. It's so neat when you're seeing it live. By the way, we're not going to do the math on this, but there you go. It's actually not that rough a math. It's more like how often is the word appearing in this little subset as opposed to the corpus, if I'm correct on that. At least that's the version I like to say. But what other algorithms? So what are you doing with SVM on this?
So FCM is another supervised, SVM is a supervised learning model that classifies data into two categories. For our purposes today, we care about the two categories of good and bad. But in my previous example, instead of cat, dog, and mouse, it would just be cat and dog, and trying to figure out how close something is to cat and dog. For instance, you might say that all of these types of cats should go in this category, or all of these types of dogs should go in another. But it could be simple as something like meow, or black, or claws, or catnip, or something else that you associate with that word. And so as you get closer and closer to words that are highly associated with your category, that's how it decides whether or not that word is a member of that group.
Very cool. All right. And then, so compare that with naive Bayes, which I probably mispronounced because I always mispronounce that one.
Yeah, honestly, it's a hard term. But basically, naive Bayes uses a conditional probability theory. So basically, it says that you're classifying data based on word frequency. So like, for instance, let's say that you have a term like, I'm going to use the cat and dog example. So I'm going to...
A lot of cats and dogs here today.
So let's say that you have a word like catnip, and you want to decide that catnip is either a characteristic of the tag cat or not a characteristic of the tag cat. Well, cat's in the name. So chances are, because of association, it's going to say that cat is associated to cat more than it's associated to not cat. And so basically what it's looking at is cat versus not cat.
So catch up might give us a little bit of a trip up.
Yes, if you spell it cats up.
Yes.
As opposed to catch up, it will probably associate it more so to cat than not.
Yeah, half the people went, yeah, and half the people went, what are you talking about? That's not how you spell it. That's really fun. All right. Oh, what's goodness gracious. Now we've got some forestry going on here. All right. Decision trees.
So decision trees is basically when you say, let's say you have, so let's say that you have an all-encompassing group, and that all-encompassing group is law. And let's say underneath that you have subgroups. So you have litigation, and then you have judge, and then you have, well, let's say litigation and let's say contracts are two subcategories. And then underneath that you have prosecutor and you have defense attorney.
Okay.
And then each different section of law will have its own prosecutor and defense attorney. So you'll say that those are your leaves, your branch is litigation and contracts, and then your trunk is the overarching group of law. So as you get new words, those new words are put underneath each different segment. So for instance, let's say you have patent. Well, patent isn't associated with litigation normally, but it is associated with contracts normally. And so as you go down, it'll be associated with law, and then it'll be associated with contracts, and then it'll be associated with whichever type of lawyer is on the receiving end, depending on the document. It's not the best example, but I hope it gives you an understanding of how you would associate it with multiple words and how that word trickles down through the leaf and the branches.
All right. In the name of going fast, I'll just mention random forest is a way of trying to do a decision tree. And you have a forest, so multiple decision trees. It randomly guesses some and tries to follow it down, speeds it up. It's to go quick on it. Random forest is oftentimes we hear it being said is better for large data sets, for big data. Is that what you got on here?
Yes, it is.
Yeah, that decision tree, if you have unlimited resource power and processing power, would be what you'd go with, but we don't. That's what I always hear. All right, but tell me about this last one down here. K nearest neighbors.
So that classifies data based on the nearest classification of previous data. For example, if you have two categories available, it looks at how similar that data is to the previously classified category. And it decides the category of the new point. So again, cat and dog, you would say, how close is it to cat? How close is it to dog? And it would decide based on what the previous data was, whether or not it's closer to cat or dog.
All right, so its name makes me immediately think of K means, but this is a little bit different. It's just number of nearest neighbors. Is that what the K means?
Yes. And so you have to specify, just like in K-means, you have to specify like how many closest data points you're looking at. So you'll say, hey, I'm taking a look at 3 or 4 or 5.
So just to give a spoiler, as somebody who works with Machine Learning Toolkit a lot, that one's not in the Machine Learning Toolkit by default.
It is not. However, it is in the scikit library. And so because we use the Python scientific computing app from Splunkbase in order to power the Python behind the machine learning toolkit, you can declare it and bring it in as its own Python file. And so you would just have to import it from that library.
Oh, very nice. I think we have more coming up about that. Ah, there we go. All right, little backstory. So, all right, what we're going to talk about, and again, I'm cognizant of our time here, so we're going to go a little faster. We're talking about Splunk, which is fantastic for search, but who watches the watcher? So if we're using Splunk to look at the searches, who looks at the searches to go, these are good and these are not? I mean, there's always, yeah, there's skip searches you can watch in the modern console. You could watch, there's a couple things out, but they're not really doing it off machine learning. I'm really interested to see your approach on doing this one. So your objective, like you said, is you're going to break it down to determine if the search is good or bad, or good or other. Like what?
Yes.
We don't want to call things bad, but optimal and non-optimal. I don't know. Maybe you like to call things good and bad. Yeah. All right. So you bring it down off the standard standard bunch of different items on best practices. So time range, you're going to check to make sure that they're not searching all the time.
So for our purposes, there are a lot of Splunk search best practices. And the truth of the matter is you could do training on each and every single one of these parameters. However, for time, and because it's easier to pick one, learn on it, then pick something else, and then learn on that, we have narrowed it down to 4 things that we're going to look at.
Okay. So we do have the list here. So if anybody goes, hey, why do you only choose those 4? It's because we were just reducing scope for the presentation. Would that be fair?
Yes.
All right. Oh, there's your 4. All right. So your first one is an index included. Always a great one for Splunk, right? Everyone knows if you don't, and you're one of those customers who have 500 indexes that are all searchable, if you put index equals star, that's massively inefficient.
Please don't use index equals star. Please.
Yeah, use index underscore star.
Nice.
All right. All right. Is a source type included? All right. That's always a good one, right? Unless you happen to be the customer who only has one source type per index, and in which case you're probably a dangerous person in society. All right. 3. I've ran into customers who do that. They'll put one source type per index. I'm like, I don't think you understand what a source type's meant for. But all right. Tell me about 3. Do your evals come before your stats?
So that goes back to the last thing on the last slide about the order of commands. You always want to make sure that your streaming commands come before your transforming commands.
Okay, so your streaming commands as in the things that will be distributed streaming commands. They'll be done on the indexers. So if you have 1,000 indexers, one search head, you want the 1,000 indexers to work on it first before it comes back to the search head?
Absolutely, because you don't want to kill your resources.
Exactly. All right, number 4, and then do you limit off fields? Ooh. What do you think about people using pipe table instead? Does that get you mad?
It does. It does.
Okay. Excellent. All right, some of your things where you can get it. So Python for scientific computing. If you go to install the machine learning toolkit, and I want you to picture the machine learning toolkit as 6 very nice custom commands and a bunch of example stuff around it to make it easy. It's there to bring people like myself, who was a Splunker, into the machine learning fold. Sometimes machine learning people or data scientists come and they're like, they have the opposite direction, that they need to figure out the Splunk part. It actually helps out with that too. When you use this, as Andrea was saying, it does require the Python for scientific computing. There is a version for Mac, a version for Linux, a version for Windows. So you install that, pop your MLTK on, and we're good to go. And then you also have an app. Oh, is the app being kept up to date? Or I used to just go to the GitHub when I go looking for these.
So if you go to it on Splunkbase, it'll take you to the GitHub, and you'll still have to download it from there.
Yeah, so it's a Splunk GitHub repository of other algorithms that just weren't in the base MLTK shipping.
Yes, and it's very useful. I would say that it helped me gain a better understanding of exactly how the machine learning toolkit was being used. Because for me, like, I normally come from the Python libraries. And so if you've ever had a Juniper notebook, you know that you have to write out the Python in the notebook. And so being able to see the underlying Python in the GitHub repository helped a lot.
All right, very cool. And then for everybody who's a Splunker and maybe you're not a Python person or not a data scientist, we can just ingest. I got my algorithm. So a lot of us don't figure out the algorithms ourselves. We stand on the shoulders of giants who've already done it. But there are a lot of folks who, like Andrea, how much do you ever go make your own algorithms because the ones you found didn't match what you wanted?
Yes. Last year I made my own command for a statistical formula called Erlang-C. It's used a lot for finding out resources needed for, honestly, call centers. But it was a great experiment of how you can create your own data science or your own statistical formula and add your own options. A lot of the machine learning toolkit allows you to default some of those parameters so that you don't have to think about the different nuances of the algorithm. But by being able to code in your own options or, just change the defaults is what makes it powerful.
Very cool. All right, so here's an example. You've got TF-IDF up here. So you're doing a fit. For anyone who doesn't do machine learning toolkit, fit is the command that we use in Splunk to grab a algorithm with your set of data that we're going to learn to create our models off of. So a model, correct me if I'm wrong, model is a collection of this is the algorithm and data, and this is how it spits it out and says, all right, based upon this data you gave me and my algorithm, this is what my models will be used. And then we take that model and we use it against other data.
Yes.
Hey, got one. All right. And SVM, of course, she already walked us through. Again, fit. Anytime you also see one of these in here, where you see the word into, you don't have to save these models. So if you're practicing in your MLTK, like, as I said, I tend to be a hack and I go, let me try these 5 different algorithms and see which one looks best. Bang, 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 test. I'm not putting them into models yet because that's saving off a lookup each time. And I don't want to have a bunch of these. So once I find the one I'm going to run with for a bit, then I'll save it off into the model. Is this how real data scientists do it? Or do you just know, or do you do what we do and try a bunch of things and see what works?
Everybody tries a bunch of things and sees what works. I think the difference between a data scientist and, your average novice is that they have an idea of why they're using it. It's not just because they'll know that certain formulas apply to certain data sets better. But even your average data scientist is going to run through 3-4 algorithms individually or in conjunction just to see if they can get the best possible fit.
Oh, that's very cool. All right. You got your decision tree classifier over here. Do watch, there are multiple decision trees in random forest inside the MLTK that we ship with, because they're not all classifiers. And real fast, can you tell us what a classifier is?
A classifier is just showing you that it's basically taking, it's the same thing. Sorry, so classifier, how can I put it? So a lot of times people don't like to say algorithm because when you say algorithm, you expect a specific type of formula. Because this is breaking it down in like that tree branch leaf format, classifier is used so that you know that the way that it's breaking it down is basically an if-then rule. So if it's a part of this group, then let's check to see if it's this group. If it's a part of this group, then let's see if it's part of this group. And so that's what is meant by classifier as opposed to an algorithm.
All right, thanks. And then also as opposed to if you just had a bunch of numeric stuff that you're not classifying, you're just popping onto a regression of some sort.
Yes.
All right. Of course, we had the random forest earlier. Oh, wait a minute. Here we go. So when I was looking through what Andrea came up with, This one is the one that drew my attention. Well, right there, and along with that one I already forgot the name of from the method earlier, but the missing algorithm here, K nearest neighbor. All right, so you have something here that is not built into Splunk machine learning toolkit.
Yes, so this is the declaration for importing the neighbors regressor into Splunk. This is a Python script. Well, it's the top part of it. It's the beginning part of where we're defining the K-neighbors regressor from the scikit library. And we're using pandas here so that we can create the data frames so that when you bring in the data, you can read it from the lookup.
Very cool. And who doesn't love pandas? They're adorable. You know, most people hear pandas and immediately think of either the black and white ones or the red pandas.
I'm
and then we're like,
the red ones.
Yeah, oh, they're cute. All right. So where do we get our data from? You're grabbing this. Now, this is back real fast. We got to specify this is because we're on a very limited scope of what we're trying to do. So we're looking for specifically, how are your searches working? And so from this, you're grabbing save searches. All right, using REST. So that goes into savesearches.conf, pulls it out, and your dashboards. All right, like both of those. Let's see. You're going and looking for ad hoc off audit. Okay, so you're all going to pay attention also to ad hoc searches then?
I think that, so for the environment that I deal with on a daily basis on the contract that I'm on, we have an enormous environment. It is many, many tens of terabytes. What we have found is that when someone creates a bad search, it takes away a lot of resources, and we often have to wait for that search to go away before it frees up those resources. And so those people tend to be what I would like to call habitual line steppers. And in order to identify those habitual line steppers, we tend to look at the audit logs to see what else they're doing in the environment.
That's very cool, because I mean, you can obviously, using the more modern Splunk items, you can limit how much impact they can have. But even then, so then they're not able to do their job necessarily because they're getting blocked out. So you use this then so that you can then have a little bit of a learning moment with them.
Yes. Yes. Right. The goal is always to educate.
Yeah, because you want them to be able to do their job.
Yes.
Yeah. All right. Very cool. And last up, I love that you got the CSV lookup in here. Andrea and I were talking a little earlier. I tend to do my machine learning toolkit stuff off of lookups. So if I have a search, like say these REST APIs, I would run it, throw it into a CSV file, then use input lookup, because as I already said, I'm going to be reiterating and doing multiple iterations, and I don't want the data to change under me. Because if I'm going to train, test, I don't want the data to change, because, well, then your model is changing with the new data that you're seeing.
True, but if you already have an established model, then running it against the REST API should be fine.
Do you find any issues with having to wait on the REST API too long? Like, do you bring it back and stash the results and then run it against the saved search?
Yes, it depends on how big a search that you're looking at, because even if you bring in so for instance, like sometimes I look at a subset of the saved searches. Like I might only look at the ones that are dealing with firewalls one day, or I might only look at ones that are dealing with proxies one day. And so depending on how big your sample size is, and also some of those saved searches can be extremely long. And so it might take just the beginning part of the search. Like if you're looking at something that has 6 sub searches in it, you might want to take it apart at a time, especially if one of the problems with the search is it's just not running or completing.
Makes perfect sense. Yeah. All right. We've only got one last slide for you, which is a quick little look. All right. So if I'm breaking down your search here, you did that input lookup. So you're grabbing, you saved the results off to a CSV, snag that in. So what are we doing here? You're doing an NLP search with a regular expression. Oh, you're doing a little pre-processing on it.
So basically what I did was I wanted it to recognize index equals and then whatever that index is as one term. And in order to do that, I created a regex in order to pull out the index of one term, which is what IDX is. And so if we pull that out as one term, and then we use TF-IDF on it, we'll find that it has a higher, basically a higher fit for those, for the index names, because it sees, I believe it sees at AWS more often within the model. And so just being able to say, hey, this is what we recognize as a term, as opposed to the app underscore without the IDX, without the index equals part of it. You're just defining that term specifically. And so the reason why I put this in here is so that whoever is, trying to replicate this at home or comes up with way better ideas than I have, they can say, okay, if I add this regex in for source type or eval or index or source or host or whatever, term you want to use this algorithm against, it will recognize that term, as opposed to it taking out those equals and separating all of the words.
Yeah, very cool. It looks like a simple little example, and then you start explaining it and you realize there's some cleverness in 3 little pipes here. So very cool. Oh yeah, go ahead.
No, I was just going to say that because Splunk is, its own search language, it's essentially its own language. And so being able to adhere to the rules of Splunk when you use this NLP example is very important.
Yeah, that's really cool. Well, Andrea, I want to thank you so much for coming and chatting with me today. She did 99.9% of this, so thanks so much for carrying me, and it's been a pleasure talking with you.
Always a pleasure, Michael. Always.
All right, folks, if you want to learn more about Machine Learning Toolkit, well, there's tons. All right, head to the community and go into the Machine Learning Toolkit rooms, so the data science rooms, or go to YouTube. There's a bunch up. All right, thank you so much. And hey, okay, I'm gonna hit you up on Teams because we got to end this for the recording to actually take.
Okay.